It's an honor to speak here. I've been to the building many times, but never to this corner of the building, which is probably not hard to believe given it's 4 blocks. So I never happened to cross this path before. But this is wonderful, and I was excited when I got the invitation to speak to you today about forecasting the Ferocious, a title that I gave to this talk a few years ago when I was forecasting tornadoes out in Oklahoma. But it also applies to a lot of other weather. So we'll go into some of that today. I've only been at the Weather Prediction Center up in College Park about 6 months, but the forecasts of flooding and extreme events we've seen just over that period of time is as challenging as the tornado forecasts that I was involved in Oklahoma. So the talk will be weighted a little bit toward the tornado forecast problem, but there are many aspects of that problem, and especially trying to forecast tornadoes that you can apply to forecasting extreme events like flash flooding. So on a day like today, you may ask, it's beautiful out. Why bother? Well, this is why. Because every once in a while, the atmosphere puts together the ingredients that can produce incredibly violent weather. And it's hard to believe sometimes when you're reviewing some of these events. Not long after moving to Oklahoma, a little over 20 years ago, I was able to go and survey some of the damage in Moore, Oklahoma after the 1999 May tornado there. And it was surreal to realize that the atmosphere can become so extreme. It looked like a bomb had gone off. And so many times, day-to-day weather is nowhere near as extreme as that. A day like today is beautiful. Many days are pretty tranquil. That you stand there in this destruction and you ponder, how can the atmosphere come to such an extreme event? And how can we better predict it? And we've been working on this for quite some time, and I'd like to say that science has advanced our capabilities to be able to anticipate these events well in advance and save lives. And in fact, there's a lot of evidence to suggest hundreds, thousands of lives have been saved with the advances of forecasting extreme weather like tornadoes and floods. But it's not a perfect science. It's far from perfect, and a lot depends on people getting the message in the right way and making the right decisions at the right time, and sometimes that's a matter of seconds. So how do we go about doing this? And it's not just tornadoes. I think the next slide here shows you some of the other aspects of extreme weather. The flooding I mentioned earlier, that top middle picture is a picture of extreme hailfall in Colorado a few years ago. The effects on aviation, we've all seen in the events and unfortunate aviation tragedies over the years, primarily due to weather. Wildfires, the middle picture there. Weather is incredibly important in predicting the nature and behavior of fire activity. Tornadoes we're mentioning. The bottom middle image is kind of close to home. I grew up in New England, and that's a picture of my dad, who's about 6 feet tall, shoveling the walkway to our farmhouse in Vermont after the super 1978 storm up in New England, which kind of was a moment of, I'm going to do this. I'm going to try to predict this stuff because it's fun, and we get school off the next day. And if you could only predict that, I don't need to do homework tonight because tomorrow will be a day off, and you got to get the forecast right. And then, of course, hurricanes and tropical weather. And so you'll see as we go through the talk how there are aspects of these events that the meteorology of these events is tied together, but essentially we approach the problem in a way of almost like baking a cake. It's a matter of assessing ingredients in the atmosphere and how those ingredients come together, what we call an ingredients-based approach to forecasting any weather, but especially severe. So a little background, the Storm Prediction Center is located on the campus of the University of Oklahoma in Norman, Oklahoma, and 20 of my little over 30 years in meteorology I spent out there with the National Weather Service. And the idea behind a National Center of Expertise is that you task meteorologists with this particularly challenging forecast day in and day out without much of a boundary. In the lower left is the map of the National Weather Service local office locations and areas of responsibility across the contiguous United States. And that responsibility includes parts of Alaska, Hawaii, and even as far out as Guam. But the local offices are relatively focused in their day-to-day forecast responsibilities, maybe covering half of a medium-sized state. And you may work in one of these offices your entire career and not necessarily be faced with the challenges of an extreme flood event or an extreme tornado event or fire weather event. And so the idea behind the national centers is to gather up expert meteorologists and put them to task on forecasting these events without boundaries, basically over the continental United States or the contiguous United States, and day in and day out gain experience. And you'll see in the talk a little later on how that experience can really pay off in terms of being able to anticipate some of the more significant events. Normally, a significant event is a rare event, and so they're not going to occur that often. So if you have a career that's focused on these particular challenges, hopefully, and you stick around and don't go crazy, like some past meteorologists have, you can get pretty good at it. But you have to learn from your mistakes, learn what you missed, completely relearn every few years the latest in science and what's going on in technology to help you do your job. And so Norman is the center of expertise essentially for tornadoes and severe thunderstorms, large hail, and high wind prediction from those thunderstorms across the U.S. So 6 months ago, a little over 6 months ago, I decided, okay, 20 years in Oklahoma, I've done my time, and it's time to come back east, where a little closer to where I grew up. And I took a position at the NOAA Center for Weather and Climate Prediction up in College Park with another national center of expertise called the Weather Prediction Center. And there, the focus is essentially precipitation forecasting for the nation, heavy snow, winter weather events, and medium range forecasting, looking out, say, 3, 4, 5, 6, 7 days in advance and trying to anticipate weather systems or the change in the weather pattern over the U.S. By looking out over the Pacific, over into Asia, and applying some of the latest information in numerical modeling to better anticipate weather in the days ahead. And it's really exciting. This is a great place to work. Great people, very dedicated to their task, very, very passionate about meteorology. And they were like that in Oklahoma too. So it sort of feels like the same type of work environment and the same type of coworkers, but a slightly different focus in the meteorology itself. So most of the talk here, I'm going to focus on what I'm calling the forecast process, and this is a combination of a number of steps, and we're going to go into each one of these steps and discuss these individually, and hopefully there'll be some questions at the end if I don't cover everything here. But it's the forecast process. I already mentioned the ingredients-based approach, but how do we assimilate all that information and move forward with an idea of what tomorrow will bring? And it's made up of conceptual models of the atmosphere, because the atmosphere is a very complex thing to understand, so we have to simplify it in terms of our understanding. Diagnosis of the current state of the atmosphere. If you don't have a good idea of what is happening right now and why in the atmosphere, then you've got little hope of making a prediction of the future. Experience, as I've already mentioned, plays a huge role in the forecast process, looking back at the past, trying to anticipate the present and the future, and then bringing all of that together. And again, looking at the ingredients, assessing their magnitudes, location, and the trend in that information, the trend in air masses, the trend in radar information, satellite information, numerical model guidance, applying statistical methods to the numerical models to come up with a forecast of the future. And we'll talk a little bit about scale and scale interaction when we get to the trend part. So what about conceptual models? Well, let's start there. If we're talking about severe weather, well, let's first talk about thunderstorms. In order to have a tornado, essentially you need a thunderstorm, and so the forecast process or the conceptual model of that breaks down to assessing the possibility of thunderstorms and then determine whether they're going to be severe. Simple, right? I think that's a very simple approach, but that starts us out and gives us the foundation to work from. So how do we do that? Well, we know that thunderstorms are convection in the atmosphere and essentially require these ingredients to exist: instability, lift, and moisture. Instability is a measure of change in temperature with height. Think of a hot air balloon. The hotter the balloon is compared to the environment it's in, the faster it will rise. And so instability is a measure of how fast an air parcel rises based on its temperature and its surroundings. Lift is crucial for thunderstorm development and sustenance. You need a mechanism to lift the air. A thunderstorm usually will not form in the absence of lift. And so by lift, we mean you've got air running into a mountain range and rising. A frontal system can move through the area and lift the air. Heating of the day can cause air to rise as well. And then finally, moisture is a crucial ingredient for thunderstorm development. And these are the three key ingredients that will get you a thunderstorm, given the right magnitudes and conditions. However, for severe thunderstorms, you need one more ingredient that's crucial, and that's vertical wind shear. Shear allows the thunderstorm to persist in the atmosphere a little longer and most likely acquire organization that will bootstrap itself into greater organization and eventually rotation and possibly even producing a tornado. If not a tornado, rotation of a thunderstorm can support stronger updrafts, which can keep ice particles higher into the storm. Those particles will acquire ice, begin to fall out of the storm, but then updrafts will push them back up, and you'll have a hailstone that will fall out eventually. Essentially what lift does is it removes the precipitation being generated by the storm away from its updraft region. And you can see in the diagram here how precipitation is falling away from the thunderstorm chimney, so to speak. And that allows this storm to acquire a duration in the atmosphere. In the absence of shear, and we've all seen it around here on a hot summer day, we may have instability, moisture, and lift. And indeed, by about 4 in the afternoon, we see thunderstorms coming up, or they come off the higher terrain to the west of us. But they don't last very long. In fact, an individual thunderstorm cell may last at most 20 minutes in its life in the absence of wind shear. It basically goes up, and it rains right onto the updraft, and it just basically kills itself off. There's no further lift instability in that environment. But shear adds that mechanism to keep the thunderstorm in a sort of organizational state where you can maintain inflow to the updraft, and as long as you've got a source of warm, moist air continuing to flow into that storm, and as long as you remove the precipitation from cutting off the updraft of that storm, it will persist. Sometimes for hours, usually while moving in a certain direction, acquiring rotation, what we call a supercell. And really what the storm is doing is it's organizing its own low pressure system, which brings in additional mass and causes lift in the atmosphere. So if those ingredients are there and the shear is in place, these storms can take on a life of their own, and usually it's not a pretty picture when that happens. So let's talk about diagnosis. We know now we have a conceptual model for the generation of a thunderstorm, and I talk primarily about those thunderstorms producing hail and tornadoes. But that persistence process also plays a crucial role in flash flooding events too. But subtle differences in how the wind shear exists in the atmosphere can play a role in a thunderstorm persisting at a single location and causing a flash flood. So let's go on to diagnosis now, the second part of our forecast process equation. And this might be where you say some of the art is still in the science of meteorology. These are hand-drawn charts of pressure and moisture and wind fields. And this allows the meteorologist, at least in my case, there are debates about whether hand analysis is a crucial component. A lot of people now say we can look at a computer screen and get this. I would argue that there is a process where I can assimilate information by doing the hand analysis in a way I can't get from a computer screen. Some would differ with that, but this is a very traditional approach to assimilating a large amount of information about the current state of the atmosphere and in putting it in a sort of a three-dimensional picture in your mind. So some of the charts here you're seeing are surface information of temperature, pressure, wind speed, and direction, frontal analysis, where's the cold front and the warm front in this image you can see here, if I've got a cursor, this is the cold front, the low pressure system. Air is streaming into the low pressure system, and the warm front is well defined here. And then we'll look above the atmosphere, look at information from balloons, radiosonde balloons, from aircraft, and basically combine that information to make a composite chart, a three-dimensional model in our mind about what the current state of the atmosphere is. We'll combine that with satellite information. Geostationary satellites are the primary tool used for satellites, although we do have polar orbiter information as well. The orange and yellow marks there are lightning strikes, cloud-to-ground lightning strikes, and then there may be analysis of what we call index parameters, measure of instability, measures of lift, measures of moisture. And again, the idea here in the diagnosis process is just like when you go to the doctor with an illness. You may not know what that illness is, the doctor doesn't know what it is, but through a process of understanding the symptoms of what the case is with your illness, they make a diagnosis. And so we can diagnose whether we're dealing with a severe thunderstorm event, a winter weather event, a flash flood event, or a tropical cyclone through this process of assimilation. One other ingredient for flooding is it usually occurs with antecedent conditions. Unlike tornadoes, most of the time a tornado can occur if you have all those other ingredients in place. Flash flooding, though, often will occur in those areas that have had a lot of rain already. So we can make some assessment of antecedent conditions with respect to flood events by looking at the amount of rainfall or soil saturation, and be particularly alert for those events that may produce excessive rainfall in an area that's experienced already a lot of rainfall. And we have what we call flash flood guidance. It's a value of how much rain can fall over the next 12, 24 hours at a particular location before we begin to have problems with runoff. So for example, I'm not sure the exact value here. If we look at the map down here on the lower right, it's about maybe 1.5 inches in 24 hours could begin to cause runoff problems. That was just I think that was from the other day. But the longer you go without rain, the higher that value is going to be. So you can see if we go a long period of time and we get into drought conditions, it may take 2 inches in 24 hours to begin to have some flooding issues. And so we look at these variables such as soil moisture and flash flood guidance to anticipate flash flood events. So moving on to experience now, we've got our model, we've got our conceptual model, we've made a diagnosis of the ingredients in the atmosphere. Now let's go back and think about, have we seen this before? The atmosphere does repeat itself, but not exactly identical. I think the atmospheric patterns are similar to fingerprints. In other words, no day is exactly the same as the last. But understanding climatology is a big part of this. This is a chart I did a few years ago about the relative risk of particular hazards given the time of year. Now, a tornado you can have just about any time of year, and even flash floods at the very top here are fairly common throughout the year. You can see why I'm not too concerned about missing something today anywhere in the country, because late October into November happens to be one of the quieter times of year. We're almost done with the tropical cyclone hurricane season in the Atlantic basin, although we have one in the Pacific today. Flash flooding is not all that common during the late fall. It can occur. It's not a non-zero chance. Heat waves are winding down. Severe weather is kind of winding down. Wildfires hopefully are beginning to diminish, although you see there is this extended peak in October, usually due to dry Santa Ana conditions in California. This is nationwide, and we're just starting to pick up the prospect of winter weather events. So out of all the times of the year, late October and November would be the time that a meteorologist might want to take a vacation somewhere. There's just not much happening normally. So experience in when can we expect these events? Not that they can't occur outside of these normal times, but when can we really expect them to ramp up? That's what this chart shows you. Specifically for tornadoes, there's actually a migratory season for tornado events. And again, tornadoes are associated with supercell thunderstorms that we just described. The conditions that support the development of those supercell thunderstorms are usually constant in a low probability sense along the Gulf Coast of the United States, parts of Florida. And then as we go into the warm season, and as we go towards spring, you'll see that area of potential actually migrates northwestward and northward up across the middle Mississippi Valley into the southern and central plains. And then by summer, it's well north across the Midwest and up across the Canadian border. And actually, if we extended this into Canada, you would actually see an area of potential even extending into the Canadian prairies as you go toward the summer months. And then it shrinks again as we go into this time of year and goes back down to the Gulf Coast. So while there's a low probability risk throughout the year along the Gulf Coast, you can see how the risk of a tornado, say in Oklahoma City, really peaks. And it's usually May into June where that peak will occur. The rest of the year is relatively quiet and not all that likely to see a tornado. As I said earlier, the atmosphere is similar on many occasions, but not identical. But we can use that similar pattern to support a look at what happened in the past. And this is an example of a forecast on the left leading up to April 27th, 2011, a devastating record tornado outbreak across parts of the southern United States and Ohio Valley. And that particular forecast is a 2-day forecast on the left. And I had a scheme that would basically go through and search, just like we do for fingerprints, basically trying to pattern match that upper air pattern there, that jet stream pattern you see on the left. It's a forecast with something that's occurred in the past. And actually, one of the better matches came up to be November 10th, 2002, which was also a pretty remarkable outbreak of tornadoes in the southern United States, and very similar in large scale, but dissimilar when it came to the specifics. And in fact, the April 27th, 2011 event is comparable to only one other event in modern times with respect to the violence and the number of significant tornadoes. But this was the November event, so NOAA was asking about 2 days ahead of the April 27th event in 2011, what's it going to look like in 2 days? What are we going to be dealing with? And I ran the analogs and I said, well, the best the likeness of this event is something that we need to be prepared for. And this was what was called the Veterans Day weekend tornado outbreak of 2002. And 83 tornadoes across 13 states and 36 fatalities, a significant tornado outbreak. It wasn't in April, but the pattern was very similar in this November event, and I basically told NOAA that, this is something we might be experiencing in a few days. Little did I know that it would be far worse, but the atmosphere put these ingredients together, similar to the other significant outbreak that we had not surpassed since 1974. So we went 37 years before the atmosphere put ingredients together in a similar fashion to what we experienced on April 27th, 2011. The April 3rd, 4th, 74 outbreak had over 200 tornadoes and over 300 fatalities, very similar to what we experienced back in 2011, and a very similar area of the country and a very similar time of year in April. And so what we might be able to take away from that, well, one, there were very few operational forecasters that worked both events. So you may go an entire career. Maybe the return frequency, let's hope, is something on the order of 30 to 50 years before we experience something like this again. But it does return. The atmosphere does put these ingredients together every so often, but let's hope it's more than 50 years away from the next one. Flooding, similar. Again, antecedent conditions play a role here, but also terrain. We know there are certain parts of the country that are susceptible to extreme flood events. Thompson Canyon is a famous canyon that's been flooded twice now in a generation out in Colorado. There are areas of Pennsylvania, Jamestown, that was 1889 when it happened. And then in July 2016, we saw Ellicott City up here, just up the road, in a particularly vulnerable area, receive about 6 inches of rain in 3 hours, causing devastating flooding in the downtown area. So in addition to these ingredients in the atmosphere coming together every once in a while, if you happen to position those ingredients in the wrong place at the wrong time, we've got a real problem. So let's go on to trend. We've done conceptual models, diagnosis, and our experience of events and brought those components to bear on the forecast process. Now let's look at what else we've got. So this is sort of bringing all of those together and then combining the current state and moving forward from there. We use what we call the forecast funnel for this, and we'll talk about this in a little detail here. So it's all connected. We go from the larger scale weather systems, air masses, high pressure systems, low pressure systems, down to cold fronts and rain bands, lake effect snow events, which are slightly smaller in scale. Maybe their lifespan is about several hours over hundreds of miles. Even smaller now, we're down to thunderstorm cells. How all of these are affected by the other ones. So air masses affect where the cold front is, the cold front will affect where the thunderstorm forms, and then ultimately down to the flood or the tornado event. And so we're talking about both a scale issue in space and time, and we're evaluating, when we're several days out, we're evaluating events over a relatively large scale, and when we get down to the details of a significant event, we're really evaluating things over minutes and just miles. Looking at some of the examples of these things, when we're talking the medium range earlier from the Weather Prediction Center, we're looking at weather systems out over the Pacific, out over even into parts of Asia. And I put the funnel on here with the star to give you some idea of where we are on the scale diagram. So this is looking over North America. It's a water vapor satellite image with frontal troughs analyzed on it. And it's basically a very dynamic pattern, but we're looking at the large scale. Will that system off the West Coast have some impact on the East Coast in the next 7 days? As that system moves from the West Coast to the central U.S., it will affect low pressure development in the central United States. That low pressure will draw moisture up from the Gulf of Mexico. The air masses will be better defined by the low in terms of the fronts that are formed from that. And we're now down into several hundred miles and a couple of days maybe in duration. That system will provide the lift, bring together the moisture, have the instability associated with it for thunderstorm formation on the what we call the mesoscale. And what I find fascinating when I go through this diagram here is the self-similarity that exists across scales. So we're talking that a very fundamental aspect of nature being that fractal nature. You have a individual thunderstorm cell that has circulations very similar to the larger low-pressure system that's driving it. And then down to the mesoscale, what we call the mesoscale low, or the mesolow associated with a supercell thunderstorm. That's a radar image there of a supercell. And this is what's known as the hook echo here. And the hook echo can be associated with an actual tornado if conditions are just right. And so what's neat about this is that that scale interaction occurs from continental hemispheric scale all the way down to the very small microscale, and then back up again too. These thunderstorm systems have a way of perturbing the atmosphere and then feeding scales back up and affecting how the large scale evolves over time. And this is an example of how that complex evolution is displayed in a satellite image. This is from Hurricane Joaquin and the incredible rainfall over South Carolina 2 years ago, or a year ago, back in October. We had a very similar event with not all that similar. Joaquin, with this event, pumped a lot of moisture in, but then moved away. We had Matthew just a couple of weeks ago bringing extreme rainfall to parts of the Carolinas. And so this scale interaction is incredibly complex. It's remarkable we do as well as we do when you look at this and say, how did we forecast 26 inches of rain given that dynamic pattern that's at play here? But we did. And some other tools that were brought to bear on the problem are ensemble forecasts. So the atmosphere can act in a variety of ways. We're not sure what those ways are necessarily ahead of time. It's what we call very sensitive to initial conditions. And so ensembles exploit that characteristic by running several different models with slightly different initial conditions. If after 48 hours the forecasts of those models look very similar, we may actually be in a regime that is predictable with some confidence. If you have a lot of different solutions after 48 hours, say for example we're forecasting the temperature in Washington, D.C. 2 days from now, and we have a forecast ensemble system, and some of the models are forecasting 30 degrees and others are 70. Well, that's a pretty wide range for 2 days out, and hopefully it will be a little closer than that. But the better agreement among ensemble system forecasts, the more confident we can be in those forecasts. And so now this technology and this science is being brought to bear on the severe weather problem. And some of the more significant events, like the April 27th, 2011 tornado outbreak, are what we call clearly evident synoptically many days in advance. We're seeing a very strong storm system come across the Pacific. We may already have moisture in place across the southern United States. And so that particular event, we had a 5-day, very confident forecast, actually 6 days in advance, before the significant tornadoes across the southern U.S. Now, the specifics are a little trickier. When somebody asks you, will a tornado move through my neighborhood at 5 p.m. this afternoon on the day of the event, you're still uncertain. And again, that goes to the scale of the problem. That can be a real challenge to be that specific, even within a few hours of the event. Another example of ensembles, we call these spaghetti charts. These are 91-member model forecasts for the upper atmospheric flow across North America, or the rainfall amounts. And right here, we've got 1-inch rainfall amounts over 24 hours, and you can see how the model has spread out that rainfall in a lot of different locations, each model having a different location. But if you were to say, well, where are you most confident of an inch of rain, you might say somewhere across northwest Louisiana into northeast Texas, because a lot of the guidance, a lot of the different models in the ensemble, the members of the ensemble, seem to agree that that's an area that will at least get 1 inch of rain. And then on the bottom is what we call the plume diagram. This is a website that I developed while at the Storm Prediction Center that looks at about 26 different models forecasting snowfall. And so you can see the range and the mean. A lot of times meteorologists will go with the mean or the consensus forecast, but it's important to know there's a lot of spread, especially as you go out in time. We also look at anomalies. I talked about the experience factor. If you've worked often at these events, you may notice something that looks really out of the ordinary, and how believable is that? And so it helps to quantify how unusual a particular parameter in the atmosphere is. How unusual is it for Washington, D.C. to have a temperature of 80 degrees in October. Very unusual this time of year. I think we're beyond the last date, but we can look at ensemble forecasts and say, well, here's a forecast of 80. How much of an agreement is there that we're actually in a regime that is that unusual? It helps the meteorologist understand whether they're really in a regime that is rare and unusual. And again, it's the rare and unusual events that probably are the most interesting and have to be paid attention to. So with respect to the products issued by the National Weather Service, we kind of follow the same concept of the forecast funnel. Several days out, we'll be talking about outlooks. Forecasts or outlooks that go out 7 days. As we get closer to the event, we're looking at those ingredients. We're doing the diagnosis of the atmosphere and describing that in mesoscale discussions. If we're really confident, we're now in a regime that will support severe storms or flooding. You'll have a flood or tornado watch issued. And then ultimately the warning will be issued if the event is realized as an observation. These are the products essentially that the Weather Prediction Center and the Storm Prediction Center specialize in. The warnings are issued by the local offices I showed on one of those initial maps, focusing on their local area and looking at radar for that information. What to do in a watch, it's pretty straightforward. I think most people understand this. There is a debate that goes raging on about whether people know the difference between watches and warnings. So just in case, a watch is not a warning. It's basically just watch out. The conditions may be coming together. It doesn't guarantee an event in your area. The environment is becoming more favorable. These are issued on forecasts, sometimes on observations, but more so as we move into advanced forecasting capability, we should be able to issue watches with some confidence with 1 to 2, 3 days of lead time. Tornado watches are usually within 6 hours or so, but flood watches and winter watches a little longer than that. So here's the climatology of severe weather watches from the Storm Prediction Center. You can see where tornado watches are most common, southeast Gulf Coast, central U.S., lower Mississippi Valley. Severe thunderstorm watches a little more common in the larger part of the country, all the way up into the northeast and up into the northern plains and even parts of the Rockies. Very rare to have tornadoes or severe storms on the west coast. They do occur, but they're usually quite isolated and brief. A warning, on the other hand, means that the event is imminent. So it's important to take action, put yourself in a place that is safe. With respect to a tornado, that's an interior room away from windows as low as you can go. You don't need a basement to survive. If you're away from windows, most tornadoes are not going to completely level the house. But the danger is imminent, so it's important to be ready to take action in the event of a warning. And these are issued by primarily observational information, radar or reports. Somebody has spotted something, something's happened. That's just a grid of warnings nationwide for tornadoes. And you can see they're relatively common in the areas of the high plains. This is usually in June. This was somewhat impacted by the 2011 event down here in the deep south. But you can see generally across from the Gulf Coast, Florida Panhandle, north and northwestward, and west-northwestward into the plains is where you're most likely to see severe thunderstorm and tornado warnings. I need to do one of these for flood warnings and see what that would look like. Probably a little more dispersed for flooding. There is a video on the web that we did a few years ago called What's a Watch? If you have anyone interested in more information, you can just Google that and it'll come up in YouTube. I want to talk a little bit about the trends in severe weather. There does appear to be, as we've seen globally, a distinct increase in the number of extreme rainfall events, both globally and across the United States. We have about 17 years worth of reliable data for the 1-inch average daily rainfall as a percentage of the continental or contiguous United States. And what's pretty remarkable is that I think it's the next slide here, 6 of the last 12 months have set all-time records. The chart is essentially a frequency distribution of the values, with the minimum values on the bottom, the max values on the top. And we hit new records over that 17-year period for area coverage of 1 inch or greater rainfall. November of last year, December, this is a fiscal year chart. We were over the max, the previous max observed in February, March, and we hit 2 new maxes in August and September. So something's going on here. You could say that the record is relatively short. There is a matter of time series. The sample size is small, but certainly seeing 6 of the last 12 months, and then even look at the months that aren't all-time maxes, every one of them is above the normal for aerial coverage of 1-inch precipitation. So it's been raining, and it's been raining a lot in a lot of different places, and I think that's Been shown here too, $6 billion flooding disasters over the last fiscal year. And primarily, a couple of these focused down in Louisiana, Texas, but we've had the West Virginia event earlier this year. South Carolina floods I showed you from Joaquin. So these are not going away, I don't think. We've got areas of drought as well in Florida or in California and other parts of the country. But when the atmosphere brings these ingredients together for extreme rainfall, we've seen what appears to be an increase in that activity, at least in the recent past. Tornadoes are a little bit more difficult to quantify in terms of trends. One thing we have noticed in recent years is quite a bit of variability and perhaps some trend to lower numbers. I don't have 2015 on here, but it was also a very low year. I wasn't quite at one standard deviation below the mean. These are EF1. These are the stronger tornadoes that make it into the record. And you can see the 2011 year there being very active. 1973 was very active. But in recent years, we've seen a drop-off in tornado activity. But I can't tell you what next year will hold. There are some general connections between ENSO, the southern oscillation, and tornado activity. We are trending toward a La Nina perhaps as we go into the winter months that could support slightly greater activity as we move into spring next year, and may see an uptick in the tornado activity. Predictions on a whole have increased in terms of, or have improved with respect to their accuracy. You see the gap here in the forecast scores for precipitation is narrowing between day 3 and day 1. Basically, a day 3 forecast today is about as good as a day 1 forecast was in 1994. And I think nobody would really dispute that. Forecast accuracy has definitely gotten better. I remember growing up and trying to anticipate snowstorms in New England, and 2 out of 3 times nothing materialized. You get all excited for nothing, but now that's a pretty rare occurrence. There's still trickiness on the northwest edge of storms, but you can be more confident in a day 2 forecast for those events. What's next? How am I doing for time? Doing okay? Okay, so we are working on global models all the time. We're looking at ensemble systems to try to exploit predictability, assess predictability in the atmosphere. I've done some work looking at environments that support severe storms out beyond 7 days, say 10, 15 days. And if we go into the cool season with weather systems better defined, especially across the Pacific, if you can assimilate that information in your global models, you might be able to get fairly confident forecasts in an ensemble sense 7 or 10 days out. Again, the devil will be in the details as to where that event will occur, but you can start to see signals if there's a lot of agreement in these ensemble systems several days in advance. The current climate forecast system model actually provides 6-hour forecasts out to 45 days, which is a little much, but it's a data junkie's dream. There's a lot of data there to look at, but it does tend to fall off in terms of its local extreme weather capability forecasts after about 10 days or so. But I have been experimenting with it. I've got an article that came out in the American Meteorological Society Bulletin last June about applying the climate forecast system guidance to longer range forecasts of severe weather, and actually it could also be applied to heavy rainfall events. It shows some skill perhaps there. There's a lot more information for weather junkies on the web. It seems like it's ever increasing. The Storm Prediction Center website is a real weather enthusiast dream. There's a lot there to look at. And the Weather Prediction Center is also an amazing place to get real-time information on the forecasts, especially precipitation, winter weather over the next week or so. And that's all I have. A lot of people help with the talk here, so just want to acknowledge them. Thanks to Laura and Karen for having me here today, Rich for the IT equipment, and it's been an honor. Thank you.
All right, we have some time for Q&A. Before we do Q&A, I just want to say these slides, WebEx and video recording, will be on the library website. It takes a little while to get the video back, but if you want to look at some of the pictures later, they'll be available for you. Click on View Past Events, and you can see everything. And for those in the room who have questions, Dave has a microphone. Anyone want to start?
You've talked about all the advancements in use of computers to do simulations and doing it that way. Has there been any change, or could you describe the technology that you use for your other sensors, other than satellites, what you use on the ground, and whether that's changing in terms of both technology and the numbers and distribution as opposed to just doing computer modeling?
Right. Well, the first thing that comes to mind, and you saw a few examples of that here, is the radar network. And the Weather Service invested in the Weather Service radar network back in the late 80s and early 90s, where they installed the Doppler radar technology across the country, 122 offices. That recently went through an upgrade to use dual polarization, which now allows the radar to not only tell you how strong or heavy rainfall or precipitation is in a particular area, and with Doppler, the wind magnitude and direction in that area to and from the radar, but actually now with dual polarization you can view the type of precipitation particles. So is it large hail or is it snow? Is it large raindrops or mist? Is it snow? Where in the cloud is that snow? So that technology has advanced tremendously, actually, since just in the last 20 years or so. And then the ability to take that information and composite it. So you have all these individual radars, but now we can take all of them and put them into one map for the United States, and we can do climatology for heavy rain events. We can do climatology of mesocyclone events using that radar data. So remotely sensed data is crucial to what we do. And the two big remotely sensed data sets are the satellite information and radar, and then the advances in electronic processing of radar signals. Yeah. Yes, right. Right.
He asked
right.
if you could take those radars and run them in real time, just for the virtual audience.
Yeah, so, right, for the online audience. Yes, that's real-time information, just like updates every 5 minutes, basically 24 hours a day. So it's an enormous amount of data, but it does update. And that information is also now being assimilated into the numerical simulations. And that's a relatively new concept, too. Only less than a decade have we had the ability to take the current radar information and put it into the simulation that's going forward in time. That shows a lot of value in short-term forecasting. Not quite sure how well that information makes for better forecasts 3 or 4 or 5 days from now, but certainly in the current scheme, the short-term forecast, the hourly forecasts for aviation and for severe weather, having that radar data assimilated into the models is crucial and is making a big advance.
Great. Anyone else in the room?
You spoke a lot about historical data and how you're using that and how you've used it. I was wondering if you're using any machine learning in this?
It's coming, and yeah, it's in a research mode more than an operational mode right now, but probably very close to being applied in an operational mode. There's a lot of things that we can apply machine learning to, given the large data sets we have now. So that is definitely being looked at. I know there have been experiments using radar information in prior storm events to provide the forecaster heads up. This storm will become severe based on the current environment and based on machine learning, the pattern that is being acquired there, and the processing that's going on to make a decision, to help with a decision. I think ultimately the best approach with these techniques is as a second set of eyes for the forecaster. Similar to the doctor and IBM's Watson, right? Because Watson is now doing medicine, right? We're going to do the same thing with weather, and it's going to be another form of information that informs the meteorologist.
So kind of following up on the question about sensors, you mentioned things like soil saturation, that sort of thing. Is that also done by radar? Or I'm working on an Internet of Things research paper right now and wondering if you guys have any other kind of sensors out there and where you see that going if you do. There's
in situ sensors for soil moisture, but there's also, in fact, I think the numerical modeling is actually initialized with satellite-based information for soil moisture. And then if you've heard of the NASA GRACE satellite mission, which is actually, it's the 2 satellites that are evaluating gravity. And when gravity changes on the surface of the Earth, there's really only one thing causing that, and that's water. And so the GRACE mission is actually measuring the changes in the water table across the face of the Earth, and could be used in a pre-flood type of data source. If we see an area that basically cannot have any more rainfall because the basin is saturated, that would be one you want to keep an eye on for the next rainfall event. And also with droughts, they've shown that gravity has diminished in parts of California with the loss of groundwater there. So the GRACE mission is a pretty interesting one and it's not even measuring the actual parameter we're interested in, but it's measuring how that impacts gravity.
Sort of related to California, someone mentioned that they live in the West Coast and fire weather is an issue there, and they are wondering if you know some of the problems associated with fire weather prediction.
Absolutely, and we didn't cover it here. We could have another talk sometime, but fire weather is impacted by a lot of things that are also looked at in terms of ingredients. So the most important being above normal temperatures and wind and low relative humidity. And we have various measures of, well, you can use those parameters individually. And you look at Southern California, if there's a wildfire outbreak in Southern California, most likely they're dealing with above normal temperatures, below normal relative humidity, and high winds. And then there are local effects. Fire weather is really interesting from the perspective of really micro scale events. You can have extreme fire behavior on elevated slopes because the fire will preheat ingredients up the slope, and if the conditions are right with wind and relative humidity and temperature, that will basically take on a life of its own, very similar to what we see with severe thunderstorms. So, fire weather is a fascinating component of severe weather meteorology. And a few years ago, we were tasked with putting a national program together in the Storm Prediction Center. A lot of people thought, why would the Storm Prediction Center be doing fire weather? Well, one of those ingredients I didn't talk about yet is lightning. And so lightning in the West is probably the primary cause of wildfire starts. And it's usually associated with what we call dry thunderstorms, very little precipitation. And so the lightning will strike, but you won't see any rainfall to put out the fire. And they've got real problems, usually in the summer out there from fire starts, remote areas that started from lightning.
Great. I'll do one more virtual, and if there's anyone else in the room, we'll get you next. What data products could you use beyond the ones that you have access to today to more accurately predict tornadoes? They're wondering about specific examples of information that you currently don't have for better accuracy.
There have been some tremendous advances beyond even what I would have expected 10 years ago in terms of our ability to predict the. Again, it's really what you're looking at in a prediction sense is the ingredients to support a severe storm or a tornado. The science is not yet at the point where it can explicitly predict a thunderstorm with a tornado. We're close. We're within 5 to 10 kilometer resolution in terms of doing that over the United States, but explicitly predicting a tornado is essentially on the scale of less than 1 kilometer, and so the modeling capability is not there yet. And one reason it's not there is we don't have the processing capability. So what you might be able to do going forward, in addition to the machine learning question, which takes a tremendous amount of processing and data to support, you need a learning set of information. But what we might be able to do going forward, if you can come up with a concept of say 5 to 10 high resolution, what we call convection allowing models over the continental United States, you may be able to begin to get ensemble or probability predictions on tornadoes at very, very specific scales. But we're not there yet. I didn't think we'd be here a decade ago, so maybe 5 years. It is really advancing very quickly. But even so, there will still be uncertainty with that. And what I've learned by looking at ensemble information is that the atmosphere is the ensemble member you don't have when you're going to make the forecast. The atmosphere, those models are not perfect, and they don't give perfect answers. And in fact, you may see some models be incredibly accurate in one part of the area. They may get the temperature and the precipitation and the snowfall perfectly in Washington, D.C., but they'll bust in Philadelphia on the same model. And you don't know going in whether you're dealing with, is that forecast in Philadelphia accurate, or the one in D.C. accurate, or are they both accurate? And so that's where you have to look at a large range of model information and make a probabilistic approach to your forecast. Or you say, well, more models are agreeing at 10 inches of snowfall here in D.C., and 5 in Philadelphia over time. And sometimes as you get closer to the event, you can get more confident, but that's also tricky because it doesn't always work that way. Sometimes your confidence can decrease as you get closer to the event. It's not linear, and that's why some folks go crazy. It's a very difficult thing to do.
Great. Anyone else in the room? Eric?
The entire topic that you're talking about sort of varies from the esoteric to the practical. And I'm curious to know where your people come from, what their disciplines are. They're obviously academics and scientists, but they're obviously, equally obviously, have to be people who have sort of an on-the-ground experience. And I'm kind of, what's your recruiting field?
That's a loaded question. We have some very
somewhat.
The folks that I work with, again, they're remarkable in their dedication. I think, like other sciences, I don't think it's unusual. People were drawn to that science, that topic at a very early age. I've met some that before they could talk their parents told them they would crawl to the window to watch the rain fall. And so it's a range of folks, but primarily it's those who, I know personally it was about science. It wasn't particularly about weather until I was into my teens, but I was always interested in science and growing up with the space and moon landings, and Apollo was fascinated by that. And it wasn't really until I realized that meteorology was an aspect. I played around with chemistry and biology, and then realized, hey, this is actually a science as well, and earth science, and that seemed to stick. So there's a lot of folks I work with, I think, have similar backgrounds, and they're just, I think, delighted to be faced with the variety of challenges every day that they get in trying to forecast significant weather. This kind of weather, it's boring, really, but it's the storms that matter. Sure. It's primarily earth science, physical science, but they may have started in other areas. I know a lot come out of physics or mathematics. There's a hell lot of heavy math in the undergraduate and graduate programs, and much more than I had when I went through. It's even emphasized more now. You have a master's degree is probably the entry level at this point, and even PhD are competitive with the openings in the Weather Service right now. So it's advanced quite dramatically in the last 25 years.
Great. We've quite a few virtual questions, and we're running out of time. Can we rapid fire through a few?
Yeah. Yep.
Does NOAA collaborate with other countries in using the models and in the predictions?
Yes.
Great.
Yeah,
Maybe
it's a global endeavor, and
Okay.
so you can't ignore the fact that other countries are doing this, and we need to collaborate.
Hurricanes were not part of your presentation, but do you have any trend prediction on hurricanes over the year?
No.
Okay.
And I should, my talk, I did put in the subtitle, I was going to speak about the other national centers. The National Hurricane Center is in Miami. They're a sister center to the Weather Prediction Center and the Storm Prediction Center. The Aviation Weather Center primarily focused on aviation and air traffic across not just the United States, but around the world. They're in Kansas City. The Space Weather Prediction Center, looking at the sun and solar storms, they're located in Boulder. And then the Ocean Prediction Center is co-located with us up in College Park. And so they're the centers of environmental prediction that compose what we call NSEP.
Great. These are two questions that I'm going to kind of combine about the same thing. What do you think the impact on severe weather prediction, the new GLM instrument on the hopefully launched soon GOES-R will be?
Yeah,
Quite
GOES-R
makes sense.
is the next generation of geostationary satellites. It was scheduled to go. It's at the Cape, being prepared for launch, hopefully later this month, maybe early December. The GLM is a global lightning mapper, so it'll be the first time that we actually have lightning strike information from a satellite. Lightning strike information has been terrestrial based through radio frequency detection finding. Now we'll have an observational platform in one location looking down on the northern hemisphere and giving us lightning strike information. So it could be revolutionary in its applications.
And they're wondering, and you kind of answered this about the expectations. So the expectations are that it's going to provide a whole new level
It will
of...
provide GOES-R in general will be providing more than a fire hose, 10 fire hoses of information now that new information that we currently don't have at higher temporal and spatial resolution than we've ever had.
How do tornado and hail predictions relate to each other?
There's a similarity in that most supercell thunderstorms produce tornadoes. So you can't get a tornado without a supercell. And a supercell thunderstorm, as I mentioned earlier, has the capability not only persist, but strengthen, and that updraft strength is what determines hail size. And so supercells are almost entirely related to hail. If you see hail larger than about a pea, it's probably a supercell thunderstorm. Not that that's going to produce a tornado, but there's a relationship to that type of thunderstorm.
Great. Can you speak to using infrasonic detection of tornadoes?
Yeah, NOAA sent out a request for science projects, research projects related to infrasonic, which is sound wave detection of tornadoes. There's some theories to suggest that just prior to a tornado touchdown, the wind speeds that are reached in a tornado may approach those of the speed of sound, and that you might be able to detect that prior to touchdown. I reviewed a number of scientific proposals where this was one of the calls for research, and I didn't see anybody putting in for it. So I'm not sure if it's a lack of research or a lack of technology to do this, or if the theory is actually that robust.
And then European prediction models are quoted frequently. Are there any fundamental differences between the approaches used by US and European models?
Fundamentally, no. The global modeling system is a numeric algorithm, and what really appears to be difference is how data is assimilated into those models. And the Europeans have built a very advanced system for model assimilation. I think that we're close, and in some cases maybe beyond that in terms of the processing power that we've now brought to bear. But fundamentally, no, there's not much difference in the numerical recipes that are used.
Okay. Anyone else in the room? Okay, I have two more, and then I'm going to call it.
Okay.
Years ago, targeted observations have been studied with the hope to improve severe weather forecast. Can you describe the potential of that approach?
So targeted observations are, for example, launching more balloons, doing intensive observations over a region that you hope when you get that information into your model, it will improve it. And just like anything in atmospheric science and prediction, sometimes that works and sometimes it doesn't. And when it doesn't, it's not always easy to understand why. And when it does, it may not be easy to understand why. It's not just about how you assimilate the information and how much you assimilate it. It's about the predictability of the atmosphere. And so you may be able to do a very intense observational period, but the atmosphere may be in a regime that is inherently unpredictable, and that's not going to help you very much. Right. And so there's a lot that we don't know.
Great. And final question. Does the agency use planetary weather data from NASA to mirror Earth weather patterns on Earth for the purpose of long-term prediction ratios?
Well, yes, and that's what climate modeling is about, is trying different scenarios. Given what we know about the atmospheric constituents and gases, we can move forward. And really, where climate modeling has shown itself capable is that they've been able to run the scenarios. They've been able to say, well, let's start the model in 1800, knowing what we know and seeing how it evolves to the current state of affairs. And current modeling capabilities have shown the ability to recreate patterns on a large scale that we have observed. And so therefore that gives a lot of credence to that approach, and it continues to be applied in more sophisticated ways.
Excellent. Thank you so much. So
Thank
informative. You. I feel like I know a little bit more about how the Capital Weather Gang comes up with the FedCast. Thank you all for coming. Again, you can view the slides and the recordings on library.doc.gov. Fill out your surveys, please. And thanks. We'll see you for the next one.
Thank you.